In everyday life, there are many technical systems that are powered either by muscle power or by tools such as motors. For example, the rear wheel of a bicycle is powered by the rider's legs. In e-bikes, the rear wheels are powered by electric motors. Another example of a system powered by muscle is a handheld drill, as used in the early days of woodworking. Today, powerful electric motors are used in drills. In all of these cases, the muscles or motors provide the energy required for the components, such as the chuck of a drill or the rear wheel of a bicycle. However, all these different examples have one thing in common. The mechanical power of motors or muscles is generally not used directly. In a bicycle, for example, the pedals are not attached directly to the rear wheel, but the rear wheel is driven by chain rings and a chain. Similarly, in a hand drill, the rotation of the crank does not directly turn the drill, but is transmitted to the drill by a ring gear and bevel gear. Even with the electric hand drill, the motor does not drive the drilling spindle directly. A look inside the drill shows that the electric motor is connected to a small gear. This so-called pinion then drives a larger gear wheel, and only then is the drill chuck set in rotation. The picture is similar for larger drill presses. Again, the electric motor is not used directly to drive the drilling spindle. In pillar drills, power is usually transmitted between the motor shaft and the drilling spindle by pulleys and belts. These examples show that in most cases a technical system is not driven directly by the motor, but, as we have seen, by gears, belts, or chains. The reason for this is that, depending on the application, the motor power must be provided in different ways, either for a high force or for a high speed. It is not possible to have both at the same time, as the everyday example of a bicycle makes very clear. For example, when starting off, the force resulting from the drive power of our legs or the motor must be as great as possible in order to set the bike in motion. That's why we usually shift into a low gear when starting off. The large forces on the rear wheel then help us to be able to start up a steep hill. However, we cannot reach high speeds in such a low gear. To do this, we have to shift into a higher gear. Then it's no longer so much about generating as much force as possible, but about reaching the highest possible speed in order to get to our destination quickly. The power of our legs or a motor can therefore be designed for maximum force on the one hand or high speed on the other. It is precisely this control between force and speed or between torque and rotational speed that is achieved by different sized sprockets. In the case of the hand drill, the necessary adjustment of the torque and speed is achieved by the differently sized gears. In the drill press, this is achieved by the different sized pulleys. These technical systems for controlling force and speed or torque and rotational speed are generally referred to as transmissions, or somewhat imprecisely, gearboxes. Transmissions are also used to control the direction of rotation. Take the reverse gear of a car, for example. Gearboxes therefore basically fulfill the following tasks: transmission of power, control of the direction of rotation, and the aforementioned control of speed and torque. Depending on the components used to create a transmission, it is referred to as a chain drive, a belt drive, or a gear train. Transmissions can also be divided into shiftable and non-shiftable transmissions. In the hand drill shown here, the speed and torque conversion of the motor cannot be changed due to the fixed dimensions of the gear wheels. This is a non-shiftable gearbox. In contrast, the conversion of speed and torque on a bicycle can be varied over a wide range by the derailleur. This chain drive is therefore a shiftable transmission. Why a gearbox can only ever increase either speed or force, but never both at the same time, is a direct consequence of the conservation of energy. In order to understand this, we will take a closer look at mechanical power in the case of translational and rotational motion. Let's look at the example of a motorized rope winch that pulls a load upwards at a constant speed. The winch drum is connected directly to the motor, so that the motor shaft drives the winch drum directly. Let us first consider the question of what motor power is required to lift a load of 200 kilograms at a lifting speed of 20 centimeters per second. To do this, we first determine the power with which the load is lifted. The mechanical power of a moving body is defined by the work done and the time taken. The more work done in a given time, the greater the mechanical power. By definition, work is the product of the force and the distance over which the force acts. If the winch pulls the load by the distance delta S with the force F within the time delta T, the power is calculated according to the formula given. The fact that the quotient of the distance traveled and the time required is equal to the speed at which the load is lifted can be used here. So note, the mechanical power P required to move a body at a constant speed V with a constant force F is the product of the two quantities. With a force of 2,000 newtons and a lifting speed of 0.2 meters per second, we get a power of 400 watts to be transferred to the load. If the friction of the rotating winch is neglected, this corresponds to the required motor power, as the motor must ultimately deliver this calculated power to the lifting load. If a greater load is to be lifted at the same lifting speed, more motor power is required. However, motors cannot provide an unlimited power. If only a certain motor power is available, it is clear from the formula just derived that a higher force can only be achieved at the expense of speed. A heavier load can therefore only be lifted with greater force if the speed is reduced accordingly. For example, if a higher force of 2,500 newtons is to be applied, a lifting speed of only 16 centimeters per second can be achieved with a maximum motor power of 400 watts. Conversely, a lighter load can be lifted at a higher speed for a given motor power. For example, with a lifting force of just 1,600 newtons, the lifting speed can be increased to 25 centimeters per second with a maximum motor power of 400 watts. This is where gearboxes come in. Gearboxes are used to control the power in favor of a higher force or a higher speed. It is therefore not possible to increase both at the same time, as this would require an increase in power. However, the power is predetermined by the motor and cannot be changed by a gearbox. So note, gearboxes do not change the mechanical power, but only the ratio between force and speed for a given power. This means either greater force at lower speed or more speed at lower force. In a perfect case, all the drive power delivered by the motor is transmitted to the output shaft of the gearbox. In reality, however, power losses occur in the gearbox due to friction. These are taken into account by an efficiency factor, which will be discussed in more detail later. The knowledge of the relationship between force and speed for translational motion can now also be applied to rotational motion. To do this, the winch is again considered. This time, however, the rotational motion of the winch is examined in more detail. Let's take a closer look at the movement of the rope as it is pulled up. The linear upward movement of the rope is converted into a rotational movement by the drum. However, the speed of the rope does not change. For example, if the rope were to wind around the drum faster than the upward movement, the rope would be stretched and eventually break. Conversely, if the rope was pulled up faster than it was wrapped around the drum, it would be compressed. The lifting speed of the translatory motion therefore also corresponds to the circumferential speed of the rotatory motion. This circumferential speed is in turn directly related to the angular speed of the rotational motion. The circumferential speed is the product of the angular velocity omega and the radius r of the circular path. Since the force always acts parallel to the circumferential speed, the power converted during the circular motion can also be determined from the product of force and speed. However, we express the circumferential speed as the product of the angular speed and the radius. In this formula, the product of force and radius corresponds to the torque acting on the drum. Let's compare the two formulas. Whereas the power of translational motion is determined by the product of force and speed, the power of rotational motion is given by the product of torque and angular speed. Here we can clearly see the respective quantities used to describe the different types of motion. While the kinematics of translational motion is characterized by speed, the kinematics of rotational motion is expressed by angular speed. The strength of this motion is described, so to speak, by the force in the case of translation, and by the torque in the case of rotation. The product of both quantities gives the power of the translational or rotational motion. Note that the angular velocity is directly related to the rotational frequency f, as shown. In engineering, the rotational frequency is also known as the rotational speed and is often denoted by the letter n instead of f. If we replace the angular speed omega in the formula for the rotational power by the expression 2 pi times n, we can see the relationship between power, torque and rotational speed of a rotary movement. In the case of the winch, this power is again supplied by the motor and is initially transferred to the drum in the form of a rotational movement. The winch then converts the rotational power into translational power. This formula shows once again that for a given motor power, the only choice is between high torque at low speed or low torque at high speed. At some point, the motor will reach its power limit and any further increase in torque can only be achieved by using a gearbox, which will then result in the aforementioned reduction in speed. So note again, gearboxes do not change mechanical power, they only change the ratio of speed to torque for a given power. This means either high torque at low speed or high speed at low torque. From an energetic point of view, It is therefore clear that an increase in torque results in a reduction in speed and vice versa. In the following, we will examine the technical way in which speed and torque are converted in a transmission. As an example, we will look at the gearbox of the hand drill, which consists of 2 gears. The small gear wheel is directly connected to the motor shaft and drives the large gear wheel, which is connected to the drilling spindle. The first thing you notice is that the large gear wheel rotates much more slowly than the small one. The reduction in rotational speed can easily be explained by the different number of teeth. The gear wheel on the drive shaft has a total of 15 teeth. When the pinion makes 1 revolution, these 15 teeth also push the driven gear on the output shaft 15 teeth further. However, the driven gear has more teeth due to its larger diameter. It is therefore not moved a full revolution for each revolution of the pinion. In this case, the driven gear has a total of 90 teeth. The pinion must therefore rotate 6 times to move the driven gear by 90 teeth, which is 1 revolution. The speed is therefore reduced to 1/6 by the 2 gears. The change in rotational speed from a driving wheel to a driven wheel is described by the transmission ratio I, also known as the gear ratio. It is defined as the ratio of the rotational speed of the driving wheel to the rotational speed of the driven wheel. In the case just described, the transmission ratio is 6, because the driving gear rotates 6 times faster than the driven gear. For gears, the transmission ratio can be determined relatively easily from the ratio of the number of teeth. Gears are characterized not only by the number of teeth, but also by their size. To characterize the size of a gear, the so-called pitch diameter is used. In simple terms, the pitch circle diameter is the diameter of imaginary cylinders that roll on top of each other without sliding. The circumferential speeds on the pitch circle of the 2 gears are therefore identical. The pitch circle diameter is referred to as such because the pitch of the teeth is based on the circumference. As the number of teeth is directly proportional to the pitch circle diameter, the transmission ratio can also be determined from the ratio of the pitch circle diameters of the 2 gears. The different number of teeth and the associated different pitch diameters not only result in the obvious change in speed, but also inevitably result in a change in torque. To understand this, let's take a closer look at the forces acting on the tooth flanks. Suppose the motor has a torque M1 that drives the pinion. The force F that this torque M1 generates on the flanks of the pinion can be determined from the pitch circle diameter D1. Note that the torque is defined as the product of force and lever arm, where the lever arm is equal to the pitch circle radius, which is half the pitch circle diameter. Solving this equation for the force F gives the following formula, which can be used to determine the force acting on the flank of the pinion. For example, assuming a motor torque of M1 equals 5 Nm and a pinion diameter of D1 equals 10 mm, the force acting on the flank of the pinion is 1000 newtons. This force of 1000 newtons now pushes the flanks of the driven gear downwards. However, as this gear wheel is considerably larger, the force also acts on a larger lever arm and therefore also produces a greater torque. With 6 times as many teeth, the driven gear wheel is also 6 times as large and therefore has a pitch diameter of 60 mm. It should be noted that the pitch diameter of gears is directly proportional to the number of teeth. This is because with double the diameter, the circumference of the gear on the pitch circle is also twice as large and therefore provides space for twice the number of teeth. Let us now calculate the torque M2 on the driven gear from the product of the force and the lever arm, where the lever arm in this case is half the pitch diameter D2. The flank force of F equals 1000 newtons resulting from the previous torque of M1 equals 5 Newton meters, now produces a torque of M2 equals 30 Newton meters on the driven gear. So while the speed is reduced to a sixth by the 2 gears, the torque increases by a factor of 6. So the torque increases to the same extent as the speed is reduced by the transmission ratio. We can also show this in general terms. To do this, we use the force formula derived earlier in the formula for calculating torque. It can now be seen that the increase in torque is equal to the ratio of the pitch circle diameters. This in turn corresponds directly to the transmission ratio I. For a given transmission ratio, the change in speed and torque can be determined as indicated. The power at the output of the transmission is equal to the power at the input. However, this is only true in an ideal case. In practice, friction causes a loss of power. These power losses are taken into account by means of a transmission efficiency factor. For spur gears, the efficiency is about 95%. The power losses also affect the torque at the output shaft of the gear unit. Since power and torque are directly proportional, A reduction in power means a reduction in torque to the same extent. Therefore, the transmission efficiency factor must also be taken into account when calculating the torque. However, the efficiency of the gearbox does not play a role in the calculation of the change in speed, because the change in speed is determined by the ratio of the number of teeth. This is because the teeth cannot penetrate each other and thus produce a lower speed than the teeth ratio dictates. In principle, a gear unit can consist not only of a single pair of gears, but also of several pairs of gears connected in series. This is called a multi-stage transmission. Each gear pair that meshes and changes speed represents a so-called gear stage. Each gear stage is characterized by a specific gear ratio resulting from the ratio of the number of teeth. In this case, the speed changes at a total of 3 pairs of gears, making it a 3-stage gearbox. The green and blue gear form the first gear stage. The green gear wheel on the first gear shaft, the so-called input shaft, has 16 teeth, while the blue gear wheel on the second gear shaft has 32 teeth. The gear ratio of this gear stage is therefore 2. The rotational speed is thus halved within this gear stage. In addition to the large gear, there is another small gear on the second shaft of the gearbox. This one also rotates at a much slower speed. Note that all gears on a gear shaft generally rotate at the same rotational speed. This small blue gear and the yellow gear now form another gear stage. In this case, the small blue gear has 15 teeth and the large yellow gear has 45 teeth, 3 times as many. Within this gear stage, the speed is reduced to 1/3. The gear ratio in the second gear stage is therefore 3. With respect to the input shaft, the third gear shaft now rotates at only 1/6 of the original rotational speed. Next to the large gear on the third gear shaft is another small gear wheel. Together with the red gear, this small yellow gear now forms the third gear stage. In this case, the small yellow gear has 24 teeth and the large red gear has 36 teeth, which means 1.5 times as many. The gear ratio in this third gear stage is therefore 1.5. With respect to the gearbox input shaft, the output shaft turns at only 1/9 of the original rotational speed. The total transmission ratio of the gearbox is therefore 9. The overall transmission ratio of a multi-stage gearbox is therefore the product of the gear ratios of the individual gear stages. It should be noted that by multiplying the individual gear ratios, each gear stage ultimately has a direct effect on the overall transmission ratio. This means, for example, that doubling or tripling the gear ratio of a gear stage also means doubling or tripling the overall transmission ratio. The overall transmission ratio of 9 in this example could, in principle, be achieved with just one gear stage. However, the gear on the output shaft would have to be 9 times larger than the gear on the input shaft. The gearbox would be large and heavy. Multi-stage gearboxes therefore offer the advantage of dividing the required ratio between several smaller gears, thus keeping the overall dimensions of the gearbox small. However, it should be noted that the influence of friction increases with each gear stage. On the one hand, this is due to the fact that more teeth mesh with each other, which generally slide against each other and therefore generate more friction. On the other hand, because the shafts of the gear stages have to be mounted and therefore cause increased bearing friction. In the case described so far, the gearbox is designed to increase torque and therefore reduce speed. In these cases, the gear ratio is always greater than 1. This is also somewhat imprecisely referred to as a power ratio. However, many technical applications also require an increase in speed. In these cases, a large gear needs to drive a smaller gear. This can be achieved by simply rotating the gearbox 180 degrees and turning the original gearbox output shaft into the gearbox input shaft. In this case, there is an increase in speed between the gearbox input and output, which inevitably leads to a reduction in torque. In this case, the gear ratio is less than 1 and this is known as a speed ratio. Shiftable transmissions, such as derailleurs on bicycles, can change the gear ratio as needed. An important characteristic of such shiftable transmissions is the increase from the minimum to the maximum transmission ratio. The greater the ratio between the maximum and minimum transmission ratio, the greater the speed range that can be shifted. This is also referred to as the transmission spread. If, for example, the maximum transmission ratio is 1.2 in the highest gear and 0.2 in the lowest gear, this results in a spread of 6. This means that the transmission ratio can be increased by a factor of 6 starting from the lowest value. With chain drives, the transmission ratio is determined in the same way as with gears, by the ratio of the diameters of the chainrings or by the ratio of the number of teeth. The main difference in power transmission is that the chainrings do not directly touch and transmit the power, but the power is transmitted through the chain. Depending on the diameter, the driving chainring pulls on the chain with a certain force due to the torque applied. With this force, the chain now pulls on a larger or smaller chainring. Therefore, the force acts on a smaller or larger lever arm and causes a change in torque depending on the gear ratio. In the case of chain drives, the change in rotational speed can again be clearly explained by the different number of teeth meshing with the chain. Again, friction only affects the change in torque, not the change in speed. Note that the chain moves at a constant speed regardless of whether it is running over a large or small chainring. Therefore, the circumferential speeds on both chainrings are always the same, only the rotational speeds are different. Belt drives use a belt instead of a chain. Power is transmitted by friction between the belt and pulley rather than by interlocking elements. The transmission ratio is determined by the ratio of the differently sized pulleys. Again, the change in torque can be explained by the different sizes of the lever arms on which the force acts, resulting in an increase or decrease in torque depending on the transmission ratio. For belt drives, the change in speed as a function of transmission ratio can be clearly explained by the different pulley circumferences. For example, when the small drive pulley completes one full revolution, it pulls the belt forward a distance equal to the circumference of the pulley. The large pulley will also move the same distance on its circumference. However, because it is larger, it will not complete a full revolution. For example, if the large pulley is twice the size and has twice the circumference, one revolution of the small pulley will move the large pulley only half a revolution. The rotational speed is therefore halved. The ratio of the pulley circumferences therefore corresponds to the change in speed. Since the pulley circumferences are directly proportional to the pulley diameters, the ratio of the circumferences equals the ratio of the diameters and therefore the transmission ratio. Friction can also be taken into account in belt drives with an efficiency factor that results in a reduction in output torque. However, unlike chain or gear drives, the elasticity of the belt affects the speed conversion. While in chain drives the chain speed and therefore the circumferential speed at the chainrings is the same, this is no longer the case in belt drives due to the elasticity of the belt. Let us first look at the belt drive in an unloaded state. For better orientation, white lines are drawn on the belt at regular intervals. Under load, the belt is now stretched considerably on the side on which it is pulled over the drive pulley. The distances between the lines increase. This belt section is also referred to as the tight side and is under high tension. In the opposite belt section, where the belt runs off the drive pulley, the belt does not have to pull any load in principle. This belt section is called the slack side and is only under low tension. The distance between the lines is significantly smaller. It should be noted that the elongation of the individual belt sections in the animation is greatly exaggerated due to the visualization. However, it illustrates the following phenomenon. As the belt passes over the drive pulley, the tension in the belt decreases. Therefore, the belt contracts as it moves around the pulley. The contracting belt then slides over the drive pulley. On the slack side, the belt moves slower than the circumferential speed of the drive pulley. This can also be seen by comparing the speed of the white lines on the tight side with the speed of the lines on the slack side. This phenomenon, where the belt slips over the pulleys due to stretching, is called slippage. When the belt runs onto the driven pulley, slippage also occurs. The tension in the belt increases from the slack side to the tight side. Therefore, the belt stretches as it moves around the pulley. The stretching belt slips over the pulley. As a result, the tight side of the belt moves faster than the circumferential speed of the driven pulley. Therefore, if the drive pulley is generally moving faster than the belt and the driven pulley is moving slower, the circumferential speeds of the pulleys will no longer be the same. Ultimately, there is a loss of speed and therefore a loss of rotational speed. The loss of speed is in the order of 1 to 2%. It should be noted that slippage only affects the speed conversion, but ultimately has no effect on the belt force and therefore on the torque conversion. However, slippage has a direct effect on power transmission because of the reduced speed. The efficiency factor also influences the power output due to the lower torque. Since slippage is due to the elasticity of the belt, it cannot be avoided. In certain applications, such as driving a printhead in 3D printers, this must be taken into account. In these cases, toothed belts, also called timing belts, can be used, which prevent slippage over the pulleys due to their positive locking design. Finally, the characteristics, advantages, and disadvantages of gear, belt, and chain drives are summarized. In gear trains, power is transmitted positively by meshing teeth. This is also the case in chain drives. In belt drives, power is transmitted by friction between the belt and the pulley. Note that with chain or belt drives, the direction of rotation is generally maintained unless, for example, a crossed belt drive is used. With gear drives, however, the direction of rotation is reversed from gear to gear. With gear drives, the backlash can be kept very small, so gear drives are very accurate in terms of speed conversion. For this reason, gears are also used for very precise control of rotary motion, such as in clockworks. With chain drives, the backlash is much greater due to the many individual chain links. In addition, as the chain rotates around the chain rings, the rigid links cause the transmission ratio to fluctuate. For belt drives, with the exception of toothed belts, slippage must be taken into account. The disadvantage of precise and therefore rigid power transmission in gear drives is their sensitivity to shock loads. The rigid gears are not able to absorb shock loads, and there is a risk of tooth flanks being damaged or even entire teeth breaking out in the event of overload. In most cases, the gear shafts and bearings are also damaged, often causing the entire gearbox to fail under overload. In contrast, belt drives have excellent damping characteristics due to the elasticity of the belt and are relatively insensitive to shock loads. In addition, belt drives have a natural overload protection because in the event of an overload, the belt simply slides over the pulleys, protecting the entire transmission from major damage. This is not the case with gear or chain drives. Gearboxes have disadvantages if large distances have to be covered between the input and output. A large number of gears must then be used, which leads to a high gearbox mass and low efficiency due to the increased flank friction. In contrast, belt and chain drives can be used with almost any shaft distance. With gear drives, however, the shaft distance is always equal to the sum of the radii of the meshing gears. Unlike belt drives, where the belt needs to be pre-tensioned to generate the necessary pressure on the pulleys, chain drives require no pre-tensioning of the chain. This reduces bearing forces accordingly. Unlike chain or gear drives, belt drives are very quiet. However, the belt is relatively sensitive to external influences such as temperature and humidity, which affect its properties such as elasticity. On the other hand, belt drives do not require lubrication and are therefore relatively low maintenance. Chain and gear drives generally require lubrication. Chain drives can only be used with parallel shafts as the chains cannot be twisted. With gear drives, the output shaft can be arranged at different angles using other gear geometries such as bevel gears, screw gears, or worms. With belt drives, the gear shafts can be at almost any angle to each other, depending on the belt used. In extreme cases, the shafts can even be arranged at an angle of 180 degrees to each other. The result is a so-called crossed belt drive. This makes it possible to change the direction of rotation. Please note that this summary only provides a rough overview. In principle, it always depends on the individual case as to which type of transmission is most suitable.